and welcome back. I hope it was not too hard yesterday. So today we are going to complete the definitions in order to define HE codes, and tomorrow we'll be seeing the asymptotic problem again and how we can improve the bounds that we had for classical codes using HE codes. So again, just to begin, the idea was to generalize Reed-Solomon codes that were, when we use the multiplicative group, we evaluate polynomials, of degree up to k minus 1, and so the code was the evaluation of this space, where evaluation means that we evaluate a polynomial in the elements of FQ star. So yesterday what we saw is that we could define in a function field, which was a finite extension of the rational function field, that we had these evaluation rings and that we have maximal ideal inside evaluation ring that was called a place associated to this ring, and that with this we could, seeing the quotient, we could define the residue class field Fp, which was O over P, and that was a field, residue class field, because P is maximal, and we said that the degree of the place was defined as the degree of this extension. So in the case where we had degree 1 place, this extension is of degree 1, so we can identify the things inside here, the residues here, as elements of FQ. So if degree of P equal 1, then Fp can be identified with F cubed. So to generalize Reed-Solomon codes, instead of using points on FQ, we are going to use places. And so what we have to do now is to find something that generalizes or to replace this space to evaluate. We need a space here that is going to be the set in which I'm going to pick my functions to evaluate here. And the evaluation is going to be the residue of the functions evaluated in points of degree 1. So that's what we are going to do today. How to define a space that generalizes this space of polynomials in which we can do the evaluation to have good things. And that are divisors. First, we are going to define divisors, and then we are going to define the Riemann rock space associated to any divisor. And from now on, I'm going to assume that the full field of constant is exactly FQ. Recall that when we define the function field, we said that we could consider FQ twiddle that were the elements of F that were algebraic. these are the elements on F that were algebraic over FQ. So my hypothesis now is going to be that this field is the field FQ. So from now on, we assume FQ2, that is, we assume that FQ is the full constant field. Of F. And we will see a result in which we need this hypothesis. So, having this said, we can define the divisor group of F, which is denoted by div of F, is the free abelian group generated for the places. So I'm going to have formal sums of places in a way that I have only left in that sum a finite amount of places. Is the free abelian group generated by the places of F. In other words, a divisor is a formal sum. A divisor is a formal sum that I can write, well, yes, you can see here, as NP times P for all the places of F, such that almost all of these coefficients are 0. So at the end, I'm only having a finite sum of places with some coefficients, where NP is an integer and almost all NP are 0. So I'm having only a finite sum here. I don't know if I said yesterday, but the set of all places of a function field is an infinite group. So, well, of course, this is a group because we have the 0 element is 0 times P, so I have all zeros. This is the 0 element of the group. And the sum is what it should be if I have two divisors, d plus d prime, which are the sum of npp plus the sum of npp. Then I can sum these two divisors, adding the coefficients here for the same place. So this is NP plus NPP. And if D is only one place with coefficient 1, which is also a divisor, we said that D is a prime divisor. Okay? And And I wanted to say something that I don't remember what. Well, don't worry. And with this, we can also define the valuation at each place. So for each, the support, that's what that I wanted to say. So if D is equal NP times P, where most of these NP are 0, then we define the support of a divisor the support is defined as the set of places such that the coefficient here is not 0. The P such that NP is not 0. So after all, what I will have is that D is the sum over support of D of the places, because all of the others are going to be 0. And this is a finite set. And so we can define a valuation, as I was saying before. If Q is one specific place of F, then we can define a valuation which is nu sub Q of a divisor is D is NPP. Then the valuation at the place Q of this divisor is going to be just the coefficient that appears in this sum in D. So if Q belongs to the support of D, this is going to be non-zero, and if this valuation is 0, it's because Q does not belong to the support. So this valuation is 0 if and only if Q is not on the support of D. If it is different from 0, then that means that I have a non-negative integer here that could be a positive integer or a negative one. And we can define, so with this definition, we can also write the divisor. We can put P in the set of places of some coefficients, or we can just write P in the support of D of the valuation at P of this divisor time P. And this is also equivalent because this is just exactly as how we define this valuation. And we have a partial ordering. We have a partial ordering in the set of divisors. And we said that two divisors, if I had D, which is the sum of NPP, and D prime, the sum of NPP, then we said that D is less or equal than D prime, if and only if, for all place P, I had that NP is less or equal than NP. So if I can compare this for all places, then I'll say that this divisor is less or equal than this other. And if I cannot compare, that's why we have a partial order and not a total one. transfer this. And so, well, in the case of a divisor in which all the coefficients are positive, we said that G is a effective divisor or a positive divisor, but it's more common to say an effective divisor. And at the end, to define codes, we can use any kind of divisors, but it's common to have effective ones. So if D is bigger or equal than 0, then D is called an effective or positive divisor. So, for example, let's return to our example that we were working yesterday, where we have that f if the rational function field. In this case, since we have places of degree 1, then we know that the fq is the full field of constant of fq of x. So our hypothesis, our general hypothesis is fulfilled. And assume that I denote by, well, remember that P infinity was the set of rational functions, which were quotients of polynomials, where the degree of the numerator was less than the degree of the denominator. And also we had other kind of places that were associated to a monic and irreducible polynomial that was P of that polynomial, the rational functions such that that polynomial does not divide the denominator, but divides the numerator. That was the other kind of places. So if I pick a linear polynomial, it's going to be a monic linear polynomial, it's going to be reducible. So we'll pick any element on FQ start. Well, it could be on FQ, could be the 0. And I will define P alpha as the place P of P minus alpha. This is going to be the rational functions such that x minus alpha does not divide G and x minus alpha does divide F. So at the end, I can write all of the elements inside P as a multiple of x minus alpha. Well, when I say a multiple, it's a multiple inside the function field, because I can have rational functions, but I need that x minus alpha does not divide any of the remaining polynomials. So I can write it as anything inside here. If I had Z belonging to P alpha, then what I have is that Z is x minus alpha to some power r times this rational function. And I know that these are coprime and none of them are divisible by x minus alpha. And now I'm assuming that r is a natural number because I want this element to be in P alpha. Okay? And recall that the evaluation of this element was that element, that power. So if we have these two places here in FQ, this is a degree 1 place. And for all of these places, we saw that, or we didn't saw it, but at least we say it. We did not prove that theorem. but we said that the degree of these places is exactly the degree of the polynomial I'm considering. So in this case, since this is a linear polynomial, then this is also a degree 1 place. So in this case, I could define, for example, a divisor D, which is 3p alpha minus 1 or 2 p infinity, for example. And this is a divisor that, for example, I cannot compare this divisor with, well, let's put another one in which we could compare. For example, if I define D prime as 4p alpha, or a prime divisor. With this prime divisor p alpha, then no, I cannot compare it because I have this. If I put like this, plus, then I will be able to compare. Because in this case, D prime is less or equal than D. Because the coefficients in p alpha is less, which is 1, is less than 3. And the coefficient for p infinity in this divisor is 0, and in this divisor is 2. So these two can be compared. But if I define this as 3p alpha minus 2p alpha, then I can compare D second and D, because this is going to be less than D, because these two are the same, and this is less than this number. But I cannot compare these two divisors. Okay? And so we need something more. One more definition associated with divisor, which is the degree of a divisor. And you can imagine how the degree of the divisor is going to be defined. Since the divisor is a finite sum of places, and every place has a degree, then of course we can define the degree of a divisor as the sum of the coefficients that I have times the degree of the place. If D is the sum of NP for some P in the support times P, then the degree of a divisor of the divisor D is defined as degree of D, which is the sum for all the places in the support of the element in P times the degree of the place. And so if I go back to the examples that I have in the other board, the degree, well, I'm going to write it here. We put the second 3p alpha minus 2p infinity. D prime was p infinity, no, p alpha. And D was 3p alpha plus 2p infinity. So the places here are all degree 1 places. So the degree of the second is going to be 3 times the degree of this place, which is 1, minus 2, the degree of this place, which is also 1. So I have 3 minus 2, which is 1. This is a degree 1 divisor. And take this in open your eyes with this, that divisors of degree 1 does not need to be prime divisors. So, for example, in this case, the degree of this place, of this divisor, sorry, is the degree of this place, which is a degree 1 place, and this is 1. And this is a prime divisor because it's only equal to 1 place and coefficient 1. But this other divisor is a degree 1 divisor, but it's not a prime divisor because in the support I'm having 2 different places. Okay? And of course, in the last case, the degree is 3 plus 2, so it's 5. And well, these are examples in which the divisors are, the support of the divisor are places of degree 1. But we could do exactly the same with places of any degree. So if I put another polynomial here instead of x minus alpha and put a monic and irreducible polynomial of degree 5, then I will have this coefficient, which is 3, times the degree of the divisor of the place. And if it is 5, then I would have 3 times 5. And that's going to be the degree of the divisor, okay? So, as you will see today, all the things that we did yesterday allowed us now to work with this, but now once you just get to work with these places, then actually it's not that hard. You don't have to be thinking every time that what we are doing is having a maximal ideal here and we are adding here. So you just get to use to do the computations. I have a question. If we have 2 support sets on the divisor such that one of them are not subsets of the other, then we can compare them. Exactly. If the supports are different, if one of them is not inside another one, then we cannot compare. That's why it's a partial ordering. Yes? For example, if I have that D is 3p alpha and D prime is 3p infinity or any other number, I cannot compare them because the support of one is not inside of the support of the other one, okay? So now we are going to define principal divisors. And we should recall that yesterday when we defined the places, we said that for each place I can define a valuation, and depending on the number that valuation have when I evaluate a function of the function field, if the valuation was positive, I said that that place was a 0 of the function c. And if it was negative, then that place was a pole. If we have a place, we associated the corresponding valuation. And for each element on the function field, a non-zero element of the function field, we said that the valuation, if the valuation was positive, we said that P is a 0 of C, and if the valuation was negative, we said that P was a pole of C. So now let's define, let C be a non-zero element and denote by C, capital C, the set of zeros of that element, and n, well, this is actually z of z. This is, this set depends on the element that I'm picking, okay? The set of poles of z, and these two sets, of course, are inside the set of places of the function field. And so with this set, I can define the zero divisor and the pole divisor of an element. So the zero divisor of an element is defined as the sum going through all the places inside the zero set of the evaluation of this, well, I'm going to put C because, sorry, like this, of the evaluation of this element times the place. So I'm going to build a divisor in which the support is just the elements that are contained in the zero set. So all of these valuations are going to be positive because I'm just picking the places in order to have positive valuations here. This is going to be an effective divisor, and it's called the zero divisor of Z. And as you can imagine, we can do the same with the poles. I can define the pole divisor of an element that it will be called, will be denoted C with an infinity. I'm putting parentheses here to denote the divisor. This is going to be the sum for the places in the set of poles. And instead of putting the evaluation, I will put minus the evaluation times the place. And why will I put minus the evaluation? Because since P is a pole of Z, then the evaluation is negative. So if I put minus the evaluation, I get a positive element. And defining like this, this will be also positive. And this pole divisor is going to be an effective divisor as well. So this is called the pole divisor of Z. And so for every non-zero element of the function field, I have a divisor defined for every element, which is the sum or the, actually I'm going to subtract the principal divisor of a non-zero element on the function field is the zero divisor minus the pole divisor. So in here, in this principal divisor, I'm taking in consideration all the zeros of the element. Oh, I put again Z and X, I'm sorry. I'm not going to use the X because I'm always using the X as the transcendental element to create, to define the rational function field. So I want to put an emphasis that this Z is any element on the function field, not that X. So here I'm taking, as I was saying, I'm taking into consideration all the zeros of Z and all the poles. And I'm adding all together, but I'm dividing into the others divisor that each of them are effective divisors. That's why I have a minus. Of course, if I put minus this with the minus of the evaluation, I will have that I'm adding the evaluations. This is just exactly the same as said that, well, I will take the sum over all the places of the function field of the evaluation of the element times the place. Because if it is a 0, it's going to be positive and it's going to be inside here. If it's negative, minus the valuation is going to be here. And if P is not a zero nor a pole, then the valuation is going to be 0. So actually, I'm having that this is the definition of the principal divisor. Okay, and we have that all of this has makes sense because I was saying that if I want this to be, I'm calling the principal divisor, but why this is a divisor? I have to check that almost all of this valuation has to be 0. Well, actually what I have is the theorem that we are not proving, that an element has a finite amount of zeros and poles. If x belongs to z except 0, then C has a finite number or amount of zeros and poles. So this is actually going to define a divisor. And of course, we are not getting in much detail for this, but we can operate with these principal divisors. Actually, you can define this set of principal divisors that is called prim of f, which are all the principal divisors for non-zero elements of the function field. And if you have, let's put w plus c, then this is w times c, and you can prove that this is all well defined. So now we can define the Riemann-Roch space, which is going to be the one that will make the part of the set of polynomials in Reed-Solomon. I will put it here in Reed-Solomon codes. So let A any divisor, and when I say any divisor, it could be a principal divisor or it could be any kind of divisor. Then we define the Riemann-Roch space associated to A space of the divisor A as this set L of A, which contain all the elements of the function field such that the principal divisor of Z is bigger or equal than minus the divisor A, and the zero element. So I have to get elements such that this divisor can be compared with this divisor A. Or, well, this is the same as saying that this sum is an effective divisor, okay? And so let's analyze what kind of functions can I have inside a Riemann-Roch space. So if I have an element inside the Riemann rock space, an element Z, let's assume that I have A, this sum, for example, NPP minus the sum of MQQ, where P and Q are places inside the support of A, and such that I put a minus here because I want that NP and MQ are positive for all P and all Q. This is inside some finite sets. Let's say it's P belonging to a finite set, I don't know, theta 1 and theta 2. Finite sets, okay? So I write A as the sum of places in which the evaluation of the divisor is non-zero, but I divide the sum in the ones which have positive valuation and the one who had negative valuation. But I put the minus outside here, so this actually is going to be a positive element. Exactly the same as I do with the principal divisors. So, please mute Hela. Well, there's some message there. I don't know what's happening. Okay, so if I have an element inside, I don't know what happened. If I have a non-zero element of the function field, and I want to see what are the characteristics of this element to be inside the Riemann rock space. If Z belongs to the Riemann rock space of A, what does that mean? That the principal divisor of A plus of C plus the divisor A is an effective divisor. So remember that this principal divisor was the zero divisor minus the pole divisor. And this divisor A can be written like this. Assume that this is called A prime, this is called A 2 prime, so A minus A second. And so I need this to be bigger or equal than 0. I need all of that sum to be effective. So what I'm telling when I have an element inside the Riemann rock space is that the things that are inside the zero divisor of the element has to compensate the elements that are here in A. And the elements that are on the pole divisor of Z has to be compensated with the element here. So this is saying that Z needs to be at least zeros on the places where A has, if this is theta 1 and this is theta 2, then what I'm saying is that C has at least zeros. Well, it would be MQ zeros. MQ zeros on the places of theta 2. So if an element is on the Riemann rock space, I need that all the places in this set, theta 2, has to be in the support of this principal divisor, and the order here has to be at least this order. It could be greater, but not less, because if I have something less, when I do the subtraction here, it's going to, I will get a negative coefficient. And the same with the pole divisor. This thing is saying that C has at most NP poles on the places of theta 1. So actually the Riemann-Roch space, what it's saying to me is that if an element is inside A, I need to have zeros where A has negative coefficients, and the order has to be at least that. And if C has poles, the poles has to be on the support of A, in where A has positive coefficients. I cannot have poles outside the support of A, because if I have poles outside the support of A, I will have something negative here that will not compensate with anything else, and so I will not have that this is positive. Okay? That's the idea. When I choose a divisor here, A, what I'm saying is in which places I'm going to allow poles, and if I want to have some zeros, then I'm going to put a negative part in this divisor just to be sure that the elements there has at least that amount of zeros. So the elements on the Riemann-Roch spaces are the element which prescribes zeros and poles in where I'm choosing on the support of the divisor A. We will see an example with the rational function field in a minute. So of course, we have this remark, which is easy to see, that an element belongs to the Riemann-Roch space of A if and only if the evaluation at P of X is bigger or equal than minus the evaluation of P at A for all P. And of course, this is going to be different from 0 for the P which are on the support of A. And we said that this is a definition. Two divisors are said to be equivalent if the difference between two of them is a principal divisor. Two divisors, let's put A and A prime, are said to be equivalent if one of them is the other plus a principal divisor. So they are equivalent if the difference of both is a principal divisor for some C in the function field minus the 0. And so this is easy to see, of course, if the divisors are no, that's a definition. What I'm saying is that we have this other remark, sorry, about the Riemann-Roch space of a divisor. And then we will see what happens when we have equivalent divisors with the Riemann-Roch spaces. This space is going to have something besides 0 if and only if we have equivalent divisors to A which is effective. So if A is an effective divisor, that could be I'm going to have a non-zero, some element here which is not 0, and if not, this is going to be different from the space with the 0 only, the trivial, if I have an effective divisor. And well, this is easy to see just looking at the definition. So before we make a break, I want to leave you this theorem, which is really easy to prove. It's just making the computations. I'm going to leave you the hints. Why I'm calling this set a space? It's because the Riemann rock space is a vector space. So the theorem is that let A be a divisor of F, that is A belongs to the divisor group. And so the first thing is that the Riemann rock space is a vector space over FQ. And the second thing is that if I had two equivalent divisors, then the Riemann rock spaces are isomorphic. So isomorphism as vector spaces. And the hint to prove this is going to be an exercise. Well, to prove that this is a vector space, you just need to have some element inside here and multiply by a constant and see that it's inside there. So you have to just work with evaluations. And the same with two elements. So you'll have to use probably, no, just working with evaluation is going to be enough. And for the second part is where you will have to use the property of principal divisors. So for the first part, it's easy to do it. You just prove that if x belongs to L of A, then AX is there, and x plus 1 is there for any A constant, and x and y in L of A. And for the second part, these are going to be the isomorphisms, phi from L of A to F, such that to any x is going to be sent to x times z, where this z, if A is A prime plus c, this is the element that I use here to define that that's isomorphism. And the inverse of that you have to prove that everything is working okay, is from L of A prime to F, and it's on the it's working in, well, it's the inverse, x times z minus 1. And here you will have to use probably that if you had x times z, this is x plus z, when we are talking about principal, I'm sorry, we are working with principal divisors, and that if you have x times z minus 1, this is x minus the principal divisor of z. So let's take a short break, like 10 minutes. So we will come back at 11:05 here, or any time that you are now, and we'll continue after that break. So If you have any doubt about the proof of the theorem I left you, then you can ask me and we can do it later, or you can send me an email as you want. But let's continue a little bit because I want to end with at least the definition of AG codes today. And so we have one more result, which is a lemma. So we have seen that the Riemann-Roch space of a divisor, it has something beside the 0 if the divisor is effective, and that if I had any divisor which is equivalent to an effective divisor, then the Riemann-Roch spaces are isomorphic. So more or less that's saying that if I have effective divisors, I have something inside the Riemann-Roch space. So what happens when I have the zero divisor, which is all zeros, or when I have a non-effective divisor? And that's what this lemma said. L of 0 is just the space of constant FQ, and if A is a negative, a non-effective divisor, then the Riemann-Roch space has only the 0 element. And so this is also easy to prove. First, if we want to prove that these two sets are the same, so let's prove first that FQ is inside the Riemann-Roch space of 0. And for this, I will have to prove that the constants are inside this set. And recall that for a divisor A, the Riemann-Roch is the set of elements such that the principal divisor is bigger or equal than minus A. Or that I could also define this using valuations. That is, that the valuation of Z is bigger or equal than minus the valuation of A, and this is for all the places of the function field. And so if we pick an element, a non-zero element of FQ, of course, if it is the 0, the valuation of the 0, we said that we know that it is infinity. And we don't have to prove anything for 0 because this is a space it's always have the 0. So 0 always belongs to L of 0. I define it, sorry, like this, okay? This was the definition. So the 0 is there. And if I pick any other element which is not 0, the valuation at any place of a constant is 0. The valuation of A is 0, which is, of course, bigger or equal than minus 0, which is the valuation of the 0 divisor. So we have that this is always happening. So what happened in the other way around? So if I pick an element, a non-zero element of L of 0, I have to prove that it is inside FQ. So let C, different from 0, an element of L of 0. So what we have is that, well, the valuation of this element is always bigger or equal than the valuation at any P of the 0 divisor. But this is 0. And of course, if this is happening for all P, then I have that this element has no pole. So C has no poles. Because a pole element was when the valuation was negative. But if this element has no poles, and we had the result that says that any transcendental element has at least one 0 and one pole, so if this element has no poles, then cannot be transcendental. So C is not transcendental. So if it's not transcendental, it's algebraic over FQ, and here we are using that the algebraic elements of FQ are inside FQ. So this is also FQ twiddle. That was our general hypothesis that we asked when we start. And so C belongs to FQ twiddle, which is FQ. So in this case, we have that if we are considering the zero divisor, what we get is only the constant. And for the other part, we want to see if A is non-effective, then, well, not only non-effective, if all the coefficients of the non-zero evaluation are negative, then the non-zero valuation are negative, then the space, the Riemann-Roch space is only the zero. And so let's assume that we have something here, and we will go to get to a contradiction. So let a non-zero element of F inside L of A. And so by the definition of L of A, we have that this principal divisor is comparable with minus A, and it's bigger or equal than that. But A was a negative divisor, so minus A is a positive 1. And so I'm saying that for all the elements, for all the places, the valuation of Z is positive. And this is for all P in a set of places. So I'm saying that this is an element that has infinitely many zeros and no poles. And this cannot happen. I cannot have an infinite amount of zeros and no poles. So the contradiction is because we assume that there was something here. And so we have nothing, and we have proved the theorem. The lemma, sorry. And the theorem that we are not going to prove that, but it's saying what happened with the principal divisors is that the principal divisor has always degree 0. The amount of zeros and the amount of pole, if we count properly, is the same in principal divisors. All principal divisors have degree 0. More precisely, if an element belongs to F, and let's remove the constant, then the degree of the zero divisor is exactly the same as the degree of the pole divisor. So when I do one minus the other, I get 0. And this is exactly the degree of this extension, the degree of the function field where I add the element Z. So for the transcendental element that define the rational function field, I would have the degree of the extension here. So the poles and the zeros are going to be the degree of the extension. And if I'm considering, for example, the rational function field, where F is FQ of X, and I'm picking exactly the transcendental element that I get to define this function field, what I get is that this is an extension of degree 1. So in that case, the element, the transcendental element that I'm adjoining to FQ to create the rational function field has a zero divisor of degree 1 and a pole divisor of degree 1. So inside the rational function field, the element X, which is creating that function field, has only one simple pole and one simple zero. Okay? And in general, for the rational function field, we call P0 to the only zero of X and P infinite to the only pole of X. And that P infinite is the P infinite that we were working earlier. So before we continue with the dimension, we have now, with this, we have all the ingredients that we need to define AG code. So we can just define AG code now. We cannot do any much with the definition only, but we can define. I want to do an example of a Riemann-Roch space, how we deal with that. And then we will see some properties about the dimension of that spaces. Up to now, we know that the Riemann-Roch space is a vector space, but we don't know anything about the dimension of that. And actually, the Riemann-Roch space is going to be a finite dimensional vector space. So it will be doing the part of the set of the space of polynomials in the Ritz-Solomon case. But in order to see that, let's see an example. I was going to leave this as an exercise, but maybe it's better if we just go through this together. I want to study the Riemann-Roch space associated to the place at infinity. In where my function field is the rational function field, as always. Okay? I'm working on this example. And recall that, as I said today, this was the space of rational functions where f and g were polynomials with coefficients on fq such that the degree of f was less than the degree of g. So I want to see if I have some non-zero element inside L of P infinity, what's the shape of this C? Using the previous results, the theorem, the proposition, the lemma, everything, what we see is, since this is an effective divisor, well, let's not put just P infinity, because if not, I'm going to get really few things, but let's put R P infinity for some natural number R. And so this divisor is an effective divisor because I'm putting here a natural number. Okay? So I know that inside this Riemann-Roch space, I have something besides 0. And so I want to see what's the shape of these elements. We know that every element on F is a rational function, a quotient of two polynomials. But can I say something more about this element? Well, the first things that we can see is, well, if C is inside this space, then the principal, let's put it, the principal divisor of Z minus RP infinity has to be an effective divisor. In particular, if we put the 0 divisor minus the pole divisor minus RP infinity, this has to be bigger or equal than 0. So actually, what we are saying is that we cannot have, am I writing okay? Yes. We cannot have here, no, sorry, plus, because it was this element, now it's okay. This is the Z bigger or equal than minus RP infinity. So I have a plus there. Okay, now it's okay. These things is saying that, well, I can have zeros whenever I want, if this is something positive, because this is an effective divisor. But on the pole divisor, I don't know why I wrote it like that. On the pole divisor of Z, we can only have the infinite, because this thing has to cancel with the things inside here. So this is saying that C only has poles at P infinity. So I cannot have any other place in the support of the zero divisor of Z. And that is saying that actually Z is not a rational function, a quotient of two polynomials, but only a polynomial. This is the same as saying that Z belongs to the ring of polynomials. And why is that? Well, assume that Z is, for example, f of x over g of x, with some polynomial with here g, which is of degree bigger than or equal than 1. So I don't have only constants. I have something else. For example, that I have a monic and irreducible polynomial that divides this, and so I can write it as 1 over p of x with this, or at some power. And so we know that the valuation at the place associated to this monic and irreducible polynomial is going to be this value here, minus this, it's going to be minus this value, because I can write this, if R is a positive element, this is P of x to minus R. So the valuation as P of Px of Z is going to be minus R, with R a positive number. And so P of x is a pole of Z. But if P of x is a pole, it should be here, inside the support of the divisor in which I'm making my Riemann-Roch space. And it's not. The only place inside the support of this divisor is the infinite. So if the only pole of the element Z is the infinite, and to have something, so if P infinity is a pole of Z, that means that Z minus 1 belongs to P infinity. And if Z minus 1 belongs to infinity, that's saying that if Z is f over g, so Z minus 1, which is g over f, belongs to P infinity, and that means that the degree of g has to be less than the degree of f. And actually, this degree has to be the 0, because this is happening for all the elements here. So inside this space, if I'm having elements inside, non-zero elements inside the Riemann-Roch space associated to P infinity, then that element is just a polynomial. And any polynomial of any degree? Well, actually, no. That's the set of polynomials of bounded degree. And the bound is going to be exactly that R. So now we know that L of R P infinity is inside this set. So if I had a non-zero element in R P infinity, that means that C is f of x, just a polynomial. And since C is inside here, what I know is that the valuation at every place of C has to be bigger or equal than minus the valuation at the place of R P infinity. And this has to happen for all P in the set of places. So we have to see two different cases. When P is the place at infinity, the infinity place, and when P is another one. If P is different from P infinity, what we have is that this valuation, the valuation at P of this divisor is 0, because this divisor is not on the support of the divisor. So what we need is that the valuation of Z at P is bigger or equal than 0. And if P is the infinity, then the valuation at P infinity of Z has to be bigger or equal than minus the valuation of at P infinity of this divisor, which is exactly R. So what I'm saying is that the valuation of this element at P infinity has to be at least minus R. But the valuation at P infinity of an element was defined. Recall that this was no, this was wrong, okay? This is only P infinity. Sorry. Recall that if this was P infinity, the valuation associated to this place was the degree of G minus the degree of F. So for any non-zero Z in F, the valuation at P infinity was defined as the degree of the, if Z was F over G, was the degree of G minus the degree of F. And so if I came here, now Z is just a polynomial. So this is the degree of the denominator, which is 0, minus the degree of the numerator. So what I need is that minus the degree of F is bigger or equal than minus R, and therefore the degree of F is less or equal than R. So the Riemann rock space associated to R times the place at infinite inside the rational function field is exactly the set of polynomials of bounded degree R. So we are recovering what we had for the Reed-Solomon codes. I'm going to erase here. We have proved with this example, we have compute here is that for a natural number R, P infinity is the set of polynomials such that degree of F is less or equal than R. So this is exactly in F equal Fq of x, okay? Only in the rational function field. This is R plus 1 as we define the set of polynomials of bounded degree R. So actually, with all of this, we could just now define, as you would imagine, the AG code as the evaluation, the classes of elements inside a Riemann rock space associated to a divisor of different rational places, rational degree 1 places, so that that residue classes are going to be inside FQ. And with that, I will be able to form words, code words, inside FQ to the n, which are going to be the words in my code. But before we just put the definition, let me say something more about these spaces. Because in this case, we could compute exactly what's the shape of this space? And we know that the space of polynomials is a finite vector space, and that the base for this space is the usual base up to degree r, which is 1x to x to the r. And so the dimension of this space is r plus 1. But in general, when we have any divisor on a function field and any function field, computing the dimension of this space is not an easy job. And first, we have to know that this is something finite, okay? So the first thing that I'm going to put that, but we are not going to prove, is that actually the Riemann-Roch space is a finite dimensional vector space. So for each divisor A of a function field f, this space L of A is a finite dimensional vector space over FQ. And again, I'm working over FQ because I want to work with codes, but all of these theories can be done over a perfect field K, and in this part, having the extra hypothesis that the K is the full field of constants, so K is algebraically closed on F. But for us, FQ is going to be more than enough. And so now that we know that if I pick any divisor on a function field, I get a finite dimensional space, I can define the dimension of a divisor, and it's going to be, the dimension of a divisor is going to be defined exactly as the dimension of the Riemann-Roch space associated to that divisor. If I have an A divisor, the dimension we define the dimension of that divisor, dimension of A as L of A. This is the dimension of A. In general, it is called L of A with this L. And this is the dimension of the Riemann-Roch space associated to A. And of course, one major problem in this theorem is to say something about this dimension for any, or for at least some kinds of divisors. And so we have some results regarding the dimension, and we have one major theorem that aims to solve this problem about the dimension of a divisor, which is the Riemann-Roch theorem that we are not going to prove, but we are going to state. So first, I want to state this proposition. Which time? Okay. The first one is, this is more or less having in consideration all of the previous results that we have already seen. If A is equivalent to another divisor A prime, we saw that the Riemann-Roch space of A was isomorphic to the Riemann-Roch space of A prime, so the dimensions has to be the same. So L of A is exactly the dimension. Two equivalent divisors have the same dimension and the same degree. And this is, and the degree of A is equal to the degree of A prime. And this is just because If they are equivalent, then they differ in a principal divisor, and the degree of a principal divisor is 0, so both of them have the same degree. So this first part is proved by all the other results that we had before. Then if the degree of A is negative, then the dimension is 0. And again, of course, this is because what we have proved, that if we have a negative divisor, then we only have the 0 inside there. And another thing is something that characterizes the principal divisors. So if I start with a divisor of degree 0, then it's going to be true that A is a principal divisor if I know that inside the Riemann-Roch space I have constants. So then the following are equivalent. And this is stated like this because this is how, well, one proved this. A is principal. 2 is that the dimension of the divisor is bigger or equal than 1. And the third is that actually it is 1. So if A is a principal divisor, the dimension of the Riemann-Roch space is 1. And here to prove this, you prove 1. If you have 1, then you have 2. 2 implies 3, and 3 implies 1. But we are not going to, well, and I have one more, which is important. Which is that if the degree of the divisor is bigger or equal than 0, then the dimension of the Riemann-Roch space is bounded by the degree of the divisor plus 1. Degree of A plus 1. And if you came back to the example that we did for the P infinity, what we got was that A was R P infinity, and we saw that L of R P infinity had dimension R plus 1, and R is exactly the degree of R P infinity. So this bound is actually sharp. It can be reached for some cases. So with this, we can define one of the most important invariants inside a function field, which is the genus of a function field. The genus of a function field F over Fq is defined by G, or sometimes we put G of F to stress that we are working on the function field F. And this is the maximum number where I count the degree of A minus the dimension of A plus 1. if I go through all the divisors of the function field. And of course, since I have this proposition, if I put this on this side, what I got that for every divisor, the degree of A plus 1 minus the dimension is always greater or equal than 0. So the genus is always a non-negative integer, because this is an integer, this is an integer, okay? So it's the maximum of that. And can I always have this element? Because this is a maximum, so I need to know that this is bounded in order to assure that we can always get the genus of the function field. And that makes sense because we have a proposition that we are not proving also. I'm sorry, I'm leaving a lot of things, but if you want to study this properly, then you need more time at least. You can study many things from the book of Tikhonov or many others. But the proposition says that there is a constant delta, a positive constant, such that the degree of A minus L of A is bounded by that constant for all A. So actually, this is bigger or equal than 0, and it's also bounded by gamma plus 1. So, well, with this only, we don't know how to compute. We don't know how to compute the genus. We don't know what the genus is. But at least we know that we can have a natural number, which is going to be the natural or 0, which is going to be the genus of a function field, and is an important invariant there. Well, now I'll put this, but it's obvious. The genus is always a non-negative integer. And so we have two important results that solve the dimension, or say something about the dimension of the of a divisor in terms of the genus. So actually, what I'm going to say is, well, you can change divisors inside the function field, but at the end, all the dimensions there are going to be related to the genus of the function field. That's with something that has to be with this quantity. And so I don't know if I want to, well, I'll do it later. So we have these three important results that I'm going to state only. One is the Riemann theorem. The second is the Riemann-Roch theorem. And the third one is a consequence of the, or a special case of the Riemann-Roch theorem, that it is going to be the case that we are going to use at the end. So the first theorem is the Riemann theorem. If we have a function field, of genus G, Then for any divisor, well, for all divisor, then for all divisor, we have that the dimension of the divisor are always bounded by the degree of A plus 1 minus G. And this is for how we define the genus, of course. But the Riemann-Roch theorem says that for each divisor, what we have is that actually the dimension of that divisor is exactly the degree of A plus 1 minus the genus plus some space here, some dimension of a space, which is W minus A, where W is a canonical divisor. And of course, I haven't defined canonical divisors, and I'm not going to do it. So this theorem is going to be like something that says nothing for us, because we don't know what this is. But I really have no time to define everything. And so you must know that this divisor is a divisor that whose degree is exactly 2g minus 2, which is the genus of the function field, and that the dimension of the Riemann-Roch space associated to a canonical divisor is exactly the genus. So the genus can be defined as the dimension of the Riemann-Roch space of a canonical divisor. But well, this theorem is not going to say much for us. But what the corollary, the thing that we are going to use is that in which case we have that this is 0, and so the dimension of the divisor is exactly this amount. And we know that if this thing is a negative divisor, then the dimension of the Riemann-Roch space was 0. So in that specific case, we are going to have that the dimension is here. And for that, what I need is that the degree of this divisor is bigger than the degree of this canonical divisor, because if the degree of this divisor is bigger than this one, I'm going to get here a negative divisor, and so the dimension is going to be 0. And so that's the result that we are going to use to bound the parameters of the AG codes when we define them. That's going to be tomorrow. But the theorem that we are going to use is that if A is a divisor of degree or such that the degree of A is bigger or equal than 2g minus 1, where g is the genus of the function field in which I'm working, then the dimension of that divisor is exactly the degree of that divisor plus 1 minus the genus. And this is because in this case, what we get is that other thing that it was supposed to be adding here, we are going to have that since the degree of W is 2g minus 2, if the degree of A is bigger or equal than 2g minus 1, this divisor is going to be a negative divisor, and so this the Riemann-Roch space associated to this divisor is going to be only the 0, and the dimension is going to be the 0. So I will be able to remove this part because this is only 0, and I'm going to get exactly the dimension of the divisor. And if I want to create an example, an example of this, I could always go to our much beloved rational function field, FQ, and there, for example, well, we can do this for any divisor, but since we have computed already the Riemann row space of the divisor R times P infinity with R a natural number, we know that the dimension of this space was R plus 1 because this was the space of polynomials of bounded degree R up to R. So the dimension is R plus 1. And so for this special divisor, the theorem says that if I pick an R bigger enough, so let G be the genus of F. And let's assume that R is something big enough in order for R to be bigger or equal than 2G minus 1. So what we have is that the dimension of the divisor, L of R P infinity, which is R plus 1, because I computed already this, is exactly the degree of the divisor, which is R times the degree of P infinity, which is 1. So this is R plus 1 minus the genus. And this is true if R is sufficiently large. But in this case, what I got is that R plus 1 has to be R plus 1 minus the genus. And so the genus of the rational function field is 0. Okay? And therefore, we had one result that, since we have been working a lot with the rational function field, I think that we should characterize this space. And then I will give you the definition of an AG code, and we will end for today. So this proposition, which is a characterization of the rational function field. So for a function field, F over FQ, the following conditions are equivalent. One is that F is a rational function field. That is, that F is exactly FQ of X. Well, this can be done also, as I said, over, it has more sense if I made it over any perfect field K, such that is the full constant field of F. Where X is a transcendental element, you know all of that. And the second is that F has genus 0. And there is some divisor A such that the degree is 1. And so we get now to the definition of the AG code. With all of that definition, all that machinery that we have built, So we will start with F, a function field over FQ. We will pick n rational places, P1 to Pn, rational places, which are different one of each other. I don't want to have many copies of the same. And remember that rational means of degree 1. We will build the divisor, which is just the sum of all of these rational places. And we will pick another divisor on the divisor group, which, whose support is disjoint with the support of D. Let G another divisor such that the support of G has not the places in the support of D. So G can be anything, but cannot contain these rational places that I'm picking here. And so the AG code is going to be the evaluation map of functions on the Riemann-Roch space of the divisor G on the rational places P1, Pn. So we have the evaluation map here. That goes from the Riemann-Roch space of G into FQ, defined as if I pick an element on the Riemann-Roch space, I send it to C of P1, the residue class, inside the residue class field, which is going to be isomorphic to FQ. I could think it inside FQ because P is a degree 1 place. P1, P2 are all degree 1 places. So I can think this, inside n copies of the finite field FQ. C of P2 up to C of Pn. And so the AG code is defined as the image of this evaluation map. We will call it C sub L of this G. This is making, I put an L here because I want to say that this construction, because you have many constructions, this construction is associated to the Riemann-Roch space of a divisor here. D is the divisor forms with the degree 1 places, so it's a divisor of degree n. And G is another divisor in which we are taking our elements in the Riemann-Roch spaces of that. Is the evaluation of L of G. So actually, the code is going to be C of P1, C of Pn, such that C belongs to the Riemann-Roch space of G. And so this is just the definition. Tomorrow we will see, well, as I said, this is actually inside FQ of n. This is a vector space inside FQ of FQn, n copies of FQ. This is just because these residue classes are inside the residue class field, which is of degree 1 because the place is of degree 1, so it's inside of Q of n. We will see the parameters of this code. As you can see, the length is going to be n. That's easy. But we are going to see what happened with the dimension and what happened with the minimum distance. And we can construct bounds for these codes. We will say that, well, of course, a base for this space is going to be needed if we want to create a generator matrix for this code. And after that, to end tomorrow, we'll see how using these codes and having sequences of codes constructing like this, we can build the Gilbert-Barsmov bound for classical codes to bound the Manning function that we saw the first class. Okay, we have to see, well, if I can get something like this, for example, which is the maximum amount of points that I can evaluate here. For example, on the Reed-Solomon code, the maximum amount of evaluating points was q minus 1 for this q. But here we will see that if we are in a function field of genus bigger than 0, then we can have more points there, more places to evaluate. And well, I hope that tomorrow will be the end of this with that showing that with this kind of definition, with these codes, we can construct sequences of long codes. So thank you very much for being here today. Hope to see you all tomorrow to our last session.